Hey everyone, and welcome. Today we're going to break down one of the slickest, most useful patterns in all of programming. I'm talking about the fast and slow pointer method. You might have also heard it called the tortoise and the hare algorithm. It's a real game changer.
So here's the plan. We'll kick things off with this simple story, the tortoise and the hare. Then we'll see how that helps us chase down cycles and lists. After that, we'll use it to split lists right down the middle, explore how it works on problems that aren't even linked lists, and finally, we'll wrap up with some code, tips, and the big takeaways.
All right, section 1, the tortoise and the hare. Let's really get the core idea down with a super simple story. This right here, this is the whole magic behind the pattern. I mean, think about it. If you have two people running on a track and one is just way faster, they're definitely going to lap the slower person, right? It's not a matter of if, it's a matter of when. A meeting is guaranteed. And that simple fact is what we're going to build everything on.
So how do we turn this into code? Well, it's pretty straightforward. We're going to create two pointers. Think of them as bookmarks that move through our data. We'll have a slow pointer that moves just one step at a time, and then we'll have a fast pointer that, you guessed it, moves 2 steps at a time. The way these two pointers eventually meet up, or don't, is what reveals all the hidden secrets about our data structure.
Okay, let's get into the classic example. The number one place you'll see this pattern pop up is for finding cycles or loops inside of linked lists. So what's the problem we're trying to solve? Imagine you have a chain of data, right? A linked list. But somewhere in that chain, one of the links, instead of pointing to the next piece of data or to the end, it actually points back to an earlier link. It's like a snake biting its own tail. And the big challenge is, how do you figure out if this loop even exists? And how do you do it without, using a ton of extra memory to keep a list of every single spot you've already been to?
And this is where our tortoise and hare come in to save the day. Here's how it works. We start both pointers at the beginning. Then we let them run. If the list is just a straight line with no loop, our fast runner is just going to zoom ahead and hit the end of the list. Race over, no cycle. But if there is a loop, the fast pointer gets trapped in it, just running in circles. And since the slow pointer will eventually enter that same loop, the fast one is guaranteed to eventually catch up from behind and lap it. When they land on the same exact spot, boom, we found our cycle.
Okay, finding the cycle is cool, but what if you need to find where the cycle starts? This is where things get really clever. So once our slow and fast pointers have met somewhere inside the loop, we do something interesting. We leave one pointer right where it is, at the meeting point. We take the other pointer and move it all the way back to the head of the list. Then we start moving them both forward again, but this time they both move at the same speed, just one step at a time. And guess what? The next place they meet is always the exact start of the loop. It's like magic, but it's math.
Let's look at the actual code for this and go. See how simple it is? It's really elegant. You've got your slow and fast pointers starting at the head, and then inside the loop, slow moves 1 step, fast moves 2. The most important part here is that for loop condition. For fast not equal to nil and fast.next not equal to nil. This is our safety net. If there's no cycle, the fast pointer will eventually hit the end, and one of these conditions will become false, stopping the loop. Without that check, our program would crash. And of course, if slow equals fast, we found it.
Okay, so this pattern is amazing for finding loops, but that's not all it can do. Not even close. It's also absolutely perfect for finding the exact middle of a list. And the best part? You can do it in just one single trip through the data.
Let's go back to our runner analogy. But this time, instead of a circular track, they're on a straight 100-meter dash. The fast runner takes off, moving twice as fast as the slow runner. By the time the fast runner crosses the finish line at 100 meters, where do you think the slow runner is going to be? Exactly. They'll be right at the 50-meter mark, the middle. It's the same exact principle.
Now, there's a small detail here that's actually pretty important. What happens if the list has an even number of items? Well, if the list has an odd number, say 5 nodes, our slow pointer lands perfectly on node number 3, the exact middle. But if the list has 6 nodes, there are kind of 2 middle nodes, right? Node 3 and node 4. With this algorithm, the slow pointer will end up on the second middle node, number 4. It's just something to keep in mind, because for certain problems, you might need the first middle one, and you'd have to adjust things a tiny bit.
So you might be thinking, okay, finding the middle is neat, but what's it good for? Well, it's a building block for solving much bigger problems. For example, if you want to check if a linked list is a palindrome, meaning it reads the same forwards and backwards, you can use this pattern. You find the middle, reverse the entire second half of the list, and then just compare the two halves. It's brilliant. It opens up a whole toolbox of other solutions.
And check this out. The code to find the middle is almost identical to the code for cycle detection.
Seriously, look at it. We initialize the slow and fast pointers the same way. The loop condition is exactly the same. The only difference is what happens after the loop finishes. Instead of returning true or false, we just return the slow pointer itself because we know it's sitting right there in the middle of the list. We're just reusing the same engine for a different purpose.
All right, we've seen cycles, we've seen midpoints. This is where the pattern goes from being a cool trick to being a true mental model, because you can use it on problems that don't look like linked lists at all. The key idea is this. Any sequence where each step determines the next one can be thought of as a linked list. It's a functional graph. Think about it. If you're transforming a number and that new number determines the next transformation, you're just following a path. If there's only a limited number of outcomes, you're eventually going to have to repeat one. And the moment you repeat an outcome, you've created a cycle. And if there's a cycle, we know how to find it.
This is so cool. Look at these two totally different problems. On the left, we have happy number, where the next step is a math calculation, summing the squares of a number's digits. On the right, we have find the duplicate number in an array, where the next step is using a value as an index to jump to the next position. They seem unrelated, but underneath they are the exact same problem. Both can create a cycle, and we can hunt it down with a slow and a fast pointer. The only thing that changes is how we define move to the next item.
And here's the code for that happy number problem. See, there's our slow and fast variable. But instead of slow next, we're calling this square sum function. So slow takes one step in the sequence, and fast takes two steps by calling the function twice. The sequence ends in one of two ways. Either we hit the number 1, which is the happy ending, or the slow and fast pointers meet up at some other number, which means we're trapped in a never-ending, not-so-happy loop, and we return false. Okay, let's bring it all home. Here are the key things you absolutely have to remember to make this pattern work for you every time.
Seriously, burn these tips into your brain. First, that check for fast doesn't equal nil and fast.next doesn't equal nil is absolutely critical. It's the #1 reason people's code crashes when they first try this. It prevents you from trying to access something that doesn't exist. Second, for finding the start of a cycle, remember that reset and resync trick. One pointer goes back to the start, and they both move one step at a time. And finally, always remember, this pattern is about the structure of the problem, the path you're following, not the actual values themselves.
So why do we go through all this trouble? Why is this pattern so famous? Well, it's because of its efficiency. It has what we call O of n, or linear time complexity. All that really means is that if your list gets twice as long, the algorithm takes about twice as long to run. It scales beautifully. It's incredibly fast because we only have to go through the list once.
And even better, it uses O of 1, or constant space. This is huge. It means it uses a fixed, tiny amount of extra memory, just enough for our 2 pointers, no matter if your list has 10 items or 10 billion items. That combination of being super fast and super light on memory is the holy grail in programming. It's why this pattern is such a classic.
So I want to leave you with this thought. This isn't just an algorithm to memorize. It's a lens. It's a new way to look at problems. The next time you see a problem that involves a sequence or steps or transformations, ask yourself, could this be a linked list in disguise? Could there be a cycle here? Once you start seeing the world in terms of these paths and cycles, you'll be amazed at how many problems you can suddenly solve.